Hello students, in previous video we have discussed the properties of maximal ideal and definition of maximal ideal. In this video I will continue to that maximal ideal properties. And in that video we have discussed that is the one properties of that. So again we will discuss this properties here, that if P is an integer, then Pz is a maximal ideal of Z if and only if P is a prime. Let us take capital M be the ideal of Pz, which is generated by this P that. So where n is, this is the number of integers that. Let us take that is P be a prime integer. We shall show that M is a maximal ideal. Let I be an ideal such that, so that definitely this maximal ideal, so which is a proper subset of this ideal that. So then since I is an ideal in Z, it is a principal ideal which is generated by positive integer. We can say that is a Q there. So then so that I it can be generated by a positive integer Q there. So this n is also integer there greater than 1, but which is what we see that now M is a proper subset of I and P is a member of M there. So that because since it is a maximal ideal, so then that implies, so definitely this P is also member of this, because obviously because every maximal ideal and every principal ideal which are the members of ideals there. So that's why M is proper subset of ideals and P is also member of ideals. So that is maximal. So definitely it is obviously this P is member of ideals there. Therefore P equal to AQ for some integer A in Z. But thing is that by the given there, P is a prime there. So that but we have achieved that that is P is because A is also in that member of I there, and then this Q is also member of I. So then obviously integers there. So both are integers. So that definitely P is integer for some prime. But thing is that which is given P is a prime there. Therefore P equal to AQ, and where Q is 1 or P equal to Q. So either one of them holds good for that, because since it is what here. So see that now Q equal to 1. So definitely obviously Q equal to 1, obviously this I is equal to integer there. Means what ideal is, it is in a is equal to, that is the integer. Suppose P equal to Q there, that is the definitely this ideal is a maximal ideal there. Therefore I equal to this ideal is it is integer, or that ideal is a maximal there. So that hence M is a maximal ideal. Now we can see that this result converse part of that one. Let M be a maximal ideal of Z, which is generated by integer P. We shall show that P is a prime integer there. See that if possible P be a composite number. Means what we can show, we can see that in a contrary there, P is a composite number, but where this P can be expressed as the product of M and N, so that but these M and N are non-unit, but these are members of integers there. Now let us take this ideal can be taken it as, it is ME, it is a product of A in Z, and M is in that integer there. Both are in integer, so that it is that. So clearly this I is also proper subset of this integer. Obviously this is also proper subset of this integer as well as this ideals there. So then as M is maximal, so as the definition, this ideal is also maximal, or this ideal is it is also in Z. Now you can take it I equal to M there. Means what? This ideal is a maximal, so then it can be this expressed as, that is the M equal to AP for some integer. It is non-unit integer there. So this A is a non-unit integer there. So then obviously this M can be taken it as, that is the Pn there. So then obvious that, so that is what you can have, that you can multiply both sides by n here. So obviously this is Apn equal to Mn there. And then you can see that P into An and that equal to Mn. So as we know that P equal to Mn, which is the product of two composite, product of that's non-unit integers there, that is P there. So P equal to P into An equal to P there, obviously there. So then when that P is non-zero, since P is non-zero, An equal to N. But thing is that this A is non-zero, non-unit, obviously N is unit there. So but it is the contrary, because which how that is where N is greater than 1. Since N is greater than 1, it is come to the contradiction, right? So that I equal to Z itself. That means ideal is integer only. That means ideal is generated by 1. So then that implies M equal to 1 also that. This second case that. So this is the second case, I equal to M and I equal to Z, we have discussed that. This I is generated by 1. Again it is a contrary, because so that definitely it is, because since A is greater than 1, so that is what it is, M equal to 1, it is not possible. So it is again contradiction there. Thus P is not a composite there. Hence P is a prime number. So we shall note on those here. So let I and J be the ideals of a ring. Then I plus J, addition of those two in ideals and product of those two ideals and intersection of those two ideals are also ideals of a R containing both I and J there. These ideals are also called the ideals generated by these I and J. Now let us take here A is a member of ring, and this can be generated, this here A can be, see that can be expressed as it as AR, that AR is small a into R, where R is in R. So then it is obviously that this A is also in R. It is also an ideal of R called the ideal of R generated by A only. Now if I is an ideal of R and take A is member of R such that A does not belongs to ideals there. So hence then this A is also an ideal of R. Hence I plus this sum of two ideals. This is an also ideal. This is also ideal. Sum of two ideals is also ideal of R there. So again that ideal I plus this A can be expressed as it as I plus AR, where I is in ideal and AR is which is generated by this A only. So then this ideal is also called the ideal generated by I union this A there. So and it is denoted by I A there. So now let us take here this, with the help of this definition we shall see that again properties of maximal ideal. Now let us take I be an ideal of a ring R, then I is a maximal ideal if and only if this I equal to R only. Suppose we can see that, suppose I is a maximal ideal of R, since A is does not belongs to ideal there, ideals, but this A is in R there. So that now this IA is what here, it is only proper subset of that R only, or that I is in this I. So because I is maximal, either one, that is I equal to IA or IA equal to R only. So first case is impossible, because since it is what here, it does because it does not belongs to I. So that's why A is does not belongs to I. So obviously A is not equal to IA there. Means what it is, this ideals can be generated by this A there. But thing is that this A is does not belongs to the ideals there. That is what which is first case, it is impossible there. So second case, only the possible there. So then this ideal, so that it is obviously A is a member of R. So obviously this IA equal to R only. So then we shall see the converse part of this one. Suppose IA equal to R, which is generated by A only, that is IA. We have to show that this I is a maximal. If suppose we can see that since it is since it is proved by that is contrary here. So if I is not maximal ideal of R, then there is some ideals J of R. Means what, we assume that I is not ideal, maximal ideal of R. So that there exist some ideals which is member of R, such that this J is either, that is I is not equal to J, because it is I is not a maximal, but J is properly, that is set of this rings there. Since I is this, I is proper subset of J there, because these are the ideals. Thus there is at least one element, that is A is member of J, such that A does not belongs to I there. So that implies I is in this here IA, and this IA is in J, because this J are the ideals there. This J, which is a member of that, obviously it is properly that is strictly in R there. So obviously IA, this is a proper subset of J, and this is proper subset of R also that. So obviously this IA is, since IA is in R there, that R that. Obviously J is R only. Means what? J equal to R, obviously this satisfied the definition of maximal. So I is the maximal ideal of R there. Now let us take another properties here. Let M be a proper ideal of a commutative ring with unity, then M is maximal if and only if R over M is a field there. So with the help of definition of field and ideals there of a commutative ring with unity, we shall prove this there. So since we assume that here, since as given here M is proper ideal of R, so then thus M is proper ideal of R there, so that obviously M is properly subset of R. But M is not always equal to R. So also R is commutative ring with unity, thus R over M is also commutative ring with the unity. We take here non-zero element, that is A plus M is also belongs to R over M. Then A is member of R, but A does not belongs to the M there. So an ideal, proper ideals there. Because A is only in M, then A plus M which is equal to M. That obviously that is which is non-zero, which is zero of that R over M there. So it is which is what we have here. Now we have to show that. So A plus M has its multiplicative inverse in R over M. So then since M is maximal ideal of R, so MA equal to R, where MA can be expressed as that is small m plus AR, where R is in R and M is in M. Since one is belongs to R and one is also belongs to MA, because MA is equal to R only. So that